Alrighty, time to do today's coding. Pretty sure I did this one on like a contest and did not actually finish it. Hopefully I don't have the same mind block on contests as I do here. Okay, so find the lexicographically largest string from box 1. Part 1. You're given a string word and integer num friends. Alice is organizing a game for her num friends. There are multiple rounds in the game where in each round the board is split into num friends non-empty strings, such that no previous round has had the exact same split. All the split words are put into the box. Find the lexicographically largest string from the box after all rounds are finished. Okay, so the word is DBCA, and the num friends is 2, so you're supposed to split up this word into 2 not empty strings. And okay, yeah, so like it could be D and then the BCA or DB and CA. And you're supposed to find the lexicographically largest string, which is the last one in the dictionary, I think. Is that what? Okay. Yeah, it's basically the last one in the dictionary. So DBC would be the biggest one if you split into 2. It has to be distinct. No, it doesn't have to be distinct. It has the exact same word is split such that no previous round has had the exact same split. No previous round? Non-empty strings. There are multiple rounds in the game. GGG, 4 friends. I wonder if there's like, if this is like one round. I don't see what the difference between rounds is. But you are supposed to split it up into num friends number of strings, non-empty strings, such that no previous round had the exact same split. Okay, well, I'm going to assume that the rounds thing, even though I don't fully understand it, might not matter. It seems like there's only one round of splitting. Okay, so what to do here? If you have a string, and you have num friends split to, it's going to be, if you think about the splits as like dividers into the word, you have num friends minus 1 dividers. So like if there's 4 friends, there's 3 dividers, and you can place them wherever as long as they're not the same. They're not in the same spot. And the 3 dividers have to be in the length minus 1. If there's some length to the string, then the number in between spots between the letters is the length minus 1. So it's like it's, yeah. If it's a 5-letter string, then there's 4 spots where you can put dividers in. Did I say? Yeah. There's length minus 1 spots, and you have num friends minus 1 dividers. Then what? Lexicographically largest string. So for each letter, the letter could be think it doesn't really matter the splits of the other friends besides the split of the friend that is besides the split of the person that gets the largest string. So I think what I should try to do is look at every largest string that's possible, and wherever that is, and take that string. So it's kind of like a maximum deal. I think this should probably be it's 10 to the third, so it's actually quite a small. I guess that's not a small sample. 5 times 10 to the third is 5,000. So I think n squared here is going to be too slow. It probably, although even n, if this was like n, like something that is O of n, linear time, then you should be able to do a longer word. So it's kind of suspicious that it's this small. But then again, I don't know. I feel like it's probably, yeah. I feel like there should be probably an O of n speed for this, like maybe a sliding window approach. So you have a current string that you might consider the longest. And then you extend that string on the left side or on the right side of the window. Let's say you have a sliding window for your string. You have left index and right index for where the ends of the string is. And like in theory, there's an upper bound to how far you can extend any given string to have enough space for other strings to be composed. So for instance, like these cases are a little too small, but let's say my string was something random. So let's say my string is random, and I'm dividing it into, let's say, friends is, the num friends is, let's say 3. That means that if I were to have the first, like, if I were to think about where the words can be composed, or what possible things can be actually assigned, R can go all the way to the D, because then the O and M can be separate substrings, separate strings for the other friends. The A can go all the way to the O, and the N can go all the way to the M, and any substring of that, and R can go to the D, A can go to the O, N can go to the M, because R and A can be the other two, and then D can go all the way to the end, or O can go all to the end, or M can go all the way to the end. So any substring of that would work as well, like R, A, and D. There are multiple rounds in the game. Organizing the game, there are multiple rounds where in each round word is split into non-empty strings such that no previous round had the exact same split. The rounds part is part of this. Find Lexicographically after all rounds are finished. Organizing. There are multiple rounds of the game where in each round word is split into such that no previous round had the exact same split. all the split words fit into the box. I don't. Feels like the multiple rounds is just like all possible combinations of splits. Okay, I'm gonna ignore the rounds thing. Pretty loud thunder outside. Okay, so I think what I just care about is creating a sliding window where the window slides pretty much as far out as possible. And the window slides out as far, not as far out as possible. If the window ever, so the first window should always be R to the D. Like it shouldn't be R, R, RA, RN, RN. It should be as far as possible. And then you compare that with the next one. So you compare A to the R, and you compare N to the R, and compare D to the R. Okay, so this is probably just too simple. So let's say the word is fantastic. And friends is still 3. So you would start off saying that your best word is like fantastic, and then A compares with the F, and that's worse. N compares with the F, and that's better because it's N is after F. So the next one would be N to the C, and then T compares with N. That's laughter, so it should be tastic. Then A compares with the T, S compares with the T, T compares with the T, and that's a tie. And then you go I compared with the A, and I is after, so it would be TIC. And TIC would be the end. So like, I'm going to do a test case here to make sure that my logic is correct there. So if it was fantastic and you're still giving it 3 friends, it should be tick is your answer. Let's see, okay. Yeah, so it's tick. Now the next question is, if I know that that's what I want to compare, is there a better way of comparing? Because in theory, like if you have a tastic compared to a tick, right, there could be multiple, it could take a very long time to do that comparison in general, basically, if you do string comparisons. Is it? I wonder how fast is string comparison? Or how fast is string comparison? Is it O of this length of the string? I'm searching for given 2 strings, return the length of the longest common prefix. Is even a question? Slice compares some Python overhead and slightly optimized memcap memory comparison, unless there's it's totally normal to interpret overhead dominates the cost of the work as a simple Python loop with C Python. Yeah, I mean, it does seem like it would be as slow as the comparison would take as long as the string lengths. There would be a limited number of comparisons. It'd be O of n comparisons, because for each string you're basically keeping a record of the best string so far and then compare it with a later string and then updating the best string, so it's like a max. Alright, I'm going to try the dummy. So, okay. Basically, this is going to be, oh gosh, this is a attempt solution, kind of a max approach. Keep best. This is the, what's it called? The largest word so far. Compare to later words. Update best if better is found. Largest will start from an index and go to maximum possible length, so that other friends can get a single letter split. Right, because if you start with R, then you go to D because you have O and M as the two other letters for your other two friends. Or you start with A, then you go to O because, again, there's two other letters. Okay. This is going to be the first attempt solution. So I'm going to say that my answer is going to be initially what? Or let's say my best so far is going to be the word starting from the first letter all the way up to, so if this is 6 letters and you need 2 left over for your other friends, then you go to 4, 0 to 4, so it'd be length minus friends minus 1. So let's say n is the size of the word. And then it'd be n minus, this is from the start to n minus friends minus 1. And then for every index in the range of 1 onwards, and indexes representing the first letter in the later thing. Index in the range of 1 to n. This is going to be the current word that you can compose that's lexicographically largest from this index. Is going to be, oh my god, splicing it from here is going to be so bad. Making so many splices. It's going to be too slow. Okay, but just for the sake of trying this, it's going to be word from the index to How many remaining friends are there? So I think I need to have remain. The number of remaining friends after this would be the numFriends minus the index. So if you have 3 friends and you're starting with the first index or index 1, then that means 1 friend has already been assigned something. If it was like you're starting at index 2, then 2 friends have been assigned. So the remaining is the numFriends minus index minus 1, because you don't include yourself. So the and I think this should be the maximum between this and 0, because you don't want negatives. So if you start, let's say this is 4 friends, and you're starting with 1 as your index, then there should be 2 remaining friends at the end. So 4 minus 1 is 3, minus another 1 is 2. Okay, I think that's right. And then the word is going to go from the index to n minus numFriends minus 1 again. So for A, we go to n is 6 minus, no, sorry, n minus remaining friends minus 1. So n is 6, remain is 2, 6 minus 2 is 4, minus 1 is 3. You should be going 0, 1, 2, 3, 4. You should be going 4. I think it's not minus 1, it's just minus remain. Okay, and then I can say if the best is bigger than the current, or let me say the current is bigger than the best, then the best should equal the current. And then I return the best. Okay, let me go ahead and just see if this is doing whatever I think it should be doing. Huh, D. Really, D. The length of the word is 4. The numFriends is 1. Or the numFriends is 2 minus 1 is 1, so it's before minus 1, which is 3. So 0, 1, 2, 3. So the first best should be DBC, right? Okay, it's not right. N is 4. numFriends is 2. 4 minus 2 is 2 minus 1. Oh, whoops. 4 minus 2 minus 1. No, that's not right. Am I confusing it with the actual length of the string? Or maybe I should be doing 4 minus numFriends. Oh, whoops. I was thinking this. 4 minus numFriends minus 1 is that, actually. Yeah. So it should be n minus numFriends plus 1. Okay, yeah. it, print empty print. Alright, let's see if, so it does seem to work. This is still too slow, I think. This splicing stuff is making it a very long copy. Numfriends is 1. I guess numfriends is 1, that should just be the word. So let's go and just skip trying to figure out how to make this other code work with that. Yeah, I assume this is going to be too slow. Really? Huh. This took me like, what, 25 minutes? Something like that? This was definitely on the contest. I was really stumped on the contest, but maybe I was overthinking it. But anyways, I mean, I guess my solution is not optimal in any sense. Let's go ahead and figure out if there's a better way of doing this. I mean, yeah, it's a pretty big difference between 23 seconds and 3 milliseconds. I think there has to be a better way than looking at creating words from everything. I guess that's a copy operation. Or, I mean, this is fine. Getting one single copy or splice from a word is fine. But doing it every single time is not. Like, that's just too slow memory-wise. Creating strings is just something that I try to avoid. Something that's probably should be avoided. Even though Python is pretty fast about it. So is there a way I can do this with like an array of integers? Like convert all the characters into some, you know, integer equivalent. A is 0, B is 1, C is 2, and then do a comparison based on those integers. Maybe. So if you had like if you have a pointer to the start of if you had a pointer to the start of where your best word is, the issue is like what word I'm thinking of that is an issue would be something like something with a lot of redundancy. Let's say it's something like that, right? And your numfriends is your number of friends is 3. So in theory, you start with something that is that as your best word, and then the next word that you compare it to would be this. So you start with this is your best, and then you have at index 1, the current is going to be this. And if you had an array of integers, you would be doing a bunch of comparisons of like 2 to 2, 2 to 2, 2 to 2, 2 to 2, until you finally reach this point where you have C compared to D, and you realize that the index 1 current word is better than the index 0 starting word. but then you have all these comparisons that are not only the same, but there are a bunch of them that are it's redundant in a very bad fashion. It's like a redundant one that you kind of already did comparison-wise, like C compared to C, and then if you even do some later ones, like this one compared to when the index is 4, again you're doing C compared to C a bunch of times. So is there a way to avoid all that? I guess if you have a bunch of the same letters, then I think you should be able to skip them. If you have a bunch of the same letters, so if you have a bunch of the same letters, it's either going to get to something that's bigger, in which case the best word will start with that bigger letter, or it's going to get to some place that is smaller, in which case the best word was already one. So if the best word was this one, right, and my later one was C starting, I think I can skip that, because eventually this D is going to be the start of the letter, the starting letter, and D would be better than C as the starting letter. And if it wasn't, let's say it was like something that was smaller, like B's at the end, then the B's would be such that this one is better, right? So you either keep the current best, or you go with something later on that is better, but it's never going to be starting with C. Okay, I think that makes sense actually. So I have my initial best word, and I strictly base on the first letter to the end. Okay, interesting. I think that's right, actually. Yeah, I think I just look at the first letter. Huh. The best is just the first letter at some index. So how do I store that? So I guess I store it based on the index. Best is just starting with index 0, and for the current index, is if the letter at the current index. So actually, let me not delete everything. Let me just keep it as reference, because I might need the indexing part. So at the best, actually. Okay, I think this was it. So let's say this is going to be second approach. Second attempt. Only need to track where the first index, where the index of the best word thus far appears, and by logic only update if a better first letter appears later on. think that's true, right? No, yeah, because it's, let's see, if it's tastic, no, I guess that's not true, because tastic, if I say that T is matching with T, the I here makes this thing look better than this, so that, fuck. So I can't just ignore everything. If it's, so I would need to compare T compared to T, and if it was something like TTA versus TTI, then I would need to compare all these T's compared to each other until I reach the A here. Until I reach the A. Compare all the T's until I reach the A. What if I condense the word into letters and how many times they repeat? Letters and how many times they repeat, so that I can skip over this comparison deal. But then what would happen if it was like TTAA, TTAA, TTAS, and TTAAI? In which case I would need to compare, I would say the T's compare and they're the same. And I compare the A's and they're the same. And then only at the S and I comparison do I know that this one is better. Oh, shucks. TTAA. Is there a way to do this with a sliding window? I have a T, I have an A, and later on I have a T, I have an A. I have a T, I have an A, versus I have a T and a T. Can I make a tree? Where I say T leads to another T, leads to A, and then for each T leads to a T. The T leads to a bigger letter, then the bigger letter will always win out. So the T has to lead to a smaller letter. So the T has to lead to an A. And if the A leads to a bigger letter, then that's fine, as long as the bigger letter is less than T. And then if A leads to a smaller letter, A is leading to I, which is still a bigger letter. So so at a certain index, you only do the number of comparisons, the minimum number of comparisons necessary. So you start with T, and you start with another T, and they're the same. So then you compare the ones, the second letters after that. So you compare the T to the A, and you say that the second T is better. And then you keep on going. Yeah, that's still going to be comparisons of the length of that you need to know in order to invalidate it. So it goes back to like something like this being an issue. Because then you compare C's with C's, C's with C's a bunch of times until you get to C compared with B, and you're keeping the same best. And you're going one down. So you, on a comparison that you've kind of already done. Huh. Oof. This is not correct. What else could you do? What else could you do? Like, I assume that there's a second version to this, part 2 from the contest. That's probably going to be harder. Or this in unoptimal solution might be an issue. So, creating words rather than going down the path of comparisons. Creating word versus going down the path of comparisons. Is there a way to go down the path of comparisons, but not all the way down? Interesting. Condensing it might be. So if it was something where you had like, instead of doing this, you say the letter and the number of times it repeats. So like C10, D3, right? So the best is currently like C10, D1. Actually, let's say C10, D5. So the starting best is going to be C10, D3 because the two friends would get D's at the end. And then the next one would be like C9, C9D, D4. Then you would know that because there's 10 C's here, so you compare 10 C's versus 9 C's, which means that the remaining C here needs compared to a D, which means that this one is better. C9D4. And that would take you, it would be faster, it would be like a couple comparisons. But then that's if it was something where the word was, you know, T2, A2, B1, T2, A2, C1, right? Or say B1, C1, and B1, E1. Then you need to say compare the T2 versus T2, A2 versus A2, and then B versus B, and then E versus C. Assuming there's other stuff before and after this to satisfy the friends, but it could just be a bunch of common letter sequences that don't necessarily even need to be repeating, but need to be compared in order to determine which one is actually larger. Ugh. So, can we make a tree out of this? A letter tree. T leads to A, leads to B, leads to E. And then when you see a later one, you say T leads to A, leads to B, leads to C. And because C is before E, then you know that it's worse. So you have a tree of different letter sequences. You have a tree of, I guess you don't even need the tree, you just need to know the index of that you're storing your best one. So you collapse it, you store your best one, and then you have to do a manual comparison. Collapse it, store the best one, do the manual comparison until you see that it's worse. Okay, let's do this. I'm gonna make a shorten, or say abbreviated array, and my abbreviated array is going to be it's going to be tuples of letter plus repeat, and then for every, let's say my letter currently is the first letter in the word, and the repeat is going to be, or I guess letter comma frequency, and the repeat is going to be initially 1 for every index in range n, where n is the length of the word. If the letter at this index equals the letter, then repeat inclusive by 1. Otherwise, I'm going to do abbreviation dot end the tuple of letter, and I guess frequency is a better thing here. Frequency. Change the current letter to be the word at this index, and change the frequency to 1. And then finally I need to do one last one of that to fence post it for the last streak. And then go ahead and just print out this, return nothing for now. And let's go ahead and put a test case. let's say it is with TTAA BETTAA C. Number of friends is, let's say, 3. This has all sorts of complications. T3, A2, B1, E1. Okay, so this is exactly what I want. Like, the complication is like I don't necessarily know. I don't necessarily know the indexing now. Like I can't just go indexing through this array because can I? Can I go indexing through this array? It's just very complicated with the number of friends and everything. Yeah, it's gonna be very complicated with the number of friends and everything. Like if the number of friends is 3, right, then the first thing that I would test would be it starts with 3 t's, and then the next thing I test is it starts with 2 t's and everything else is the same. Or like or counting how many I extend to is gonna be difficult. Like I'd say the number of friends was something big, like yeah, let's say the number of friends was 100 friends, and your ending tuples were like, you know, a bunch of 1s, 2s, and 3s. Then how far do you actually? You figure out how to know what the ending spot might be. It's just too complicated, I think. Or that's like a problem in this, a difficult problem in and of itself. If you have like 100 friends and let's say there's 50 remaining friends in the thing, like how far can you extend this thing to? How far you need to compare it to? All right, I think I'm going to take a break from this. I'll post this as, or I'll wrap this one up as my unoptimal solution and think about it later. But this is definitely not optimal. Basically, it's going to revolve around for any starting index in Word to have the best, or for any starting index word, the largest lexicographically largest word from that index will be the max, will always have the maximum size, you know, because longer size, longer length beats shorter length. For lexicographically. Thus can and size can be determined based on number of friends, each getting a smallest, like 1-letter string. So therefore, can keep track of best word up to certain index and compare that and update that if current word starting from index beats it. Does require creating or splicing n words from initial word to do comparisons, which is rather slow. And also doing string comparisons require like O of string length time in general, which is, you know, in some situations you might consider it constant, but in this situation I don't think that's reasonable. And so you start with your best word. It's starting with the letter index 0 all the way up to like you have enough space for your friends or the remaining friends, so num friends minus 1 away from the end. And then for every other index, I calculate the number of remaining friends. It could be actually 0 remaining friends because there's enough letters before this to cover them. And then you do the current word based on starting with this index to the n minus the remaining, and then do the update, and then return the thing. Time complexity, this can be O of, I want to say this is almost O of n squared. Since, I mean, it's kind of a fast O of n squared, but since say O of n where n equals the length of word, not even based on the number of friends. The number of friends can be whatever. Since it requires creating n strings for comparisons and doing n length and doing comparisons of strings that are n length. Base complexity, this is going to be O of n as well to keep the best word.